Hi everyone. There are a number of absentees these few days, so I've decided to do a lesson recording of all the slides that I'm going to use in Term 3 Week 1, and possibly some of the slides may be used in Term 3 Week 3 when you're back in school. So in this week, we are revising the topics that we have covered during HBL period. So it would be good that you take out your relevant materials as you look through this lesson lectures. Okay, so for this part, there are a series of three videos. The first one is on revision for forces, mass and weight, and the other two will be for moments and pressure. So please take out your notes for types of forces, or I think it's called interaction of forces. So have it next to you so that you can follow as I move along. So one thing about this, one thing to remember about this chapter is to be able to calculate resultant forces. So this is a revision of how you can calculate resultant forces. You may want to pause your video right now and see if you could do the three questions. And then after that, you can then proceed to listen to the explanation and see if you got the answers right. Okay, so for part A, the resultant force for A and B. So to calculate resultant force, we are not too concerned whether the forces act on the right side or the left side, the top or the bottom of the object. What is important is the direction that they are acting. So therefore, over here, you can see that a 10 Newton force is acting to the right, and then the 6 and 4 Newtons are acting to the left. So I'm going to add up the same direction together. So 6 plus 4, so that's 10 Newtons. And then the other one is also 10 Newtons. Okay, so you have 10 Newtons acting to the right and 10 Newtons acting towards the left. And therefore, the resultant force, which I'm going to write as F with a subscript R, will be 10 minus 10. So you end up with 0 Newtons. So you can say that the resultant force is 0, or there is no resultant force. For B, if you look at the arrowheads, again, this and this are in the same direction. So there will be 9 Newtons to the right. So to the right hand side is 9 Newtons. And to the left is 3 Newtons. Okay, to the left is 3 Newtons. So to find the resultant force, what we have to do is we will take the big minus the small. Okay, so we have, this is the bigger force, right? 9. So 9 minus 3. So we have 6 Newtons. All resultant force you need, okay, the resultant force you need to give a direction. So the direction you'll follow the bigger force. Okay, so this here. So the answer is 6 Newtons to the left. Let's look at C. Now C is not so straightforward, so read the questions carefully, okay? Now for C, the question asks for the amount of F. Okay, so the question is asking you what is F if the resultant force is 10 Newton upwards. So we need to do a little bit of work here. Let's first of all calculate the total downward force. So the total downward force will be 20 plus 15, right? So that will be 35 Newtons. And the upward force, just use another color, the upward force is F. I don't know what that is. I know it's F. And I do know that these two forces, they interact with one another, and they will give you, a resultant force of 10 Newtons and upwards. Because this is what the question said, 10 Newtons upwards. So your resultant force is 10 Newton upwards. So because the resultant force is upwards, so I would know that the upward force is bigger than the downward force. All right, because the resultant force always follows the direction of the resultant force always follows the direction of the bigger force. So in this case, the bigger force will then be F. So which means normally if I were to calculate resultant force, then I'll take the bigger force, which is F, and then I minus the downward force, 35, I will get 10. So this is the rest of mathematics, right? So F will be equals to 10 plus 35. So then you get 45 Newtons upwards. And of course, what you can do is you just substitute 45 over here, and you see whether you will end up with this resultant force of 10 newtons upwards, which you should. Let's take a look at this. Now, I've given some examples in this lesson where I have taken a look at the quiz that you all have done during HBL and taken out the questions that many of you have gotten it wrong, you know, the commonly wrongly answered questions. And I put it into this set of revision materials so that you can relook at the question again, and hopefully this time you get it right. Now, in this question, many of you got it wrong. I think only about 30% of the students got it right. Perhaps you're careless. Let's read. So the question says that there are three forces acting here, and there is a fourth force. I don't know what that fourth force is. I don't even know where it's acting, but I know that it's the last force here. I didn't draw arrow because I don't even know which direction is acting, but I know there's one more force. Okay, this is the fourth force. And when this fourth force is applied, the box will remain stationary. So the question asks for the magnitude and the direction of this fourth force. When I say magnitude, magnitude simply means what is the value. So 2 newtons is a magnitude, 10 newtons is a magnitude. So all these are magnitudes, okay? So when we are talking about forces, we need to give a magnitude, but we also need to give a force. So to do this question, what we need to do is we first of all, we know that there are three forces acting on the box. So what we will do is we will find the resultant force first. So we have 6 newtons, we have 6 and 8, right, to the right hand side. So we add up. So the right hand, so in this case, the right hand side, 6 plus 8, so that's 14 newtons. Then what about the left hand side? The left hand side, sorry, not at the left hand side, towards the left. So towards the left is 4 newtons. Okay, so then I can simplify this into something like this. So 14, and then this is 4. So I know that this is the resultant force, 10 newtons. Okay, so the meaning of saying that this is the resultant force of 10 That's why it's up this way. Okay, and this one also away from the object. And you always draw it on the string that is provided. Right. So now that we know the resultant force is 10 newtons to the right hand side, uh, we will be able to know what is the force that we need in order to make this stationary. So instead of writing all these three forces now, 1, 2, 3, they have been represented by 10 newtons, which is the resultant of all these three. So a result of all these three forces, um, the box will behave as if it is being pulled to the right with a 10 newton force. So in order for it to remain stationary, then I will have to pull it to apply a force, also 10 newtons to the left. Then I will get a resultant force of 0. So therefore, this F here, the fourth force, F, should be 10 newtons. Sorry, it should be 10 newtons to the right, to the left. Okay. So this is how you do it. So do read the question very carefully, because a lot of students thought that the question is asking you to find the resultant force, but actually is to find the force that will keep the box stationary. Now, I'm going to go on to the next part, talking about how to draw free body diagrams. Now, free body diagram basically is just a term um, to mean to draw forces acting on an object. Okay, so therefore, you can start by looking at these three diagrams and ask yourself, do you know that these three diagrams are all drawn wrongly? Do you know why they are wrong? If you're not sure why they are wrong, then you may have to listen to the next few slides carefully so that you can come back again and see if you could do the question. So before that, do note that there are two types of forces, contact and non-contact. There are four forces that you need to know how to draw. And they are friction, tension, okay, normal contact force. So all these three are contact forces. There is also one non-contact force that you have to learn how to draw, which is gravitational force. Or I can use the word interchangeably, right? So I can take weight to be the same as gravitational force. So these are the four forces that you must learn how to draw. They are not difficult, but you just have to follow the instructions very clearly. Now, this is when you cannot afford to be creative, okay? Because there's a set of rules on how to draw each and every one of these force, and you have to follow it to the T, right? So how do you draw weight? Now, every object that is given to you, you would need to draw the gravitational force, the weight, because there will always be gravitational force acting on objects on Earth. So you need to remember that when you are drawing, you need to draw from the center of gravity. Don't worry so much about this term center of gravity. You can just draw from the center of your object. So can you see? This is where the center is. Okay. And your line to show gravitational force should be a vertical line downwards. All right. So it should be vertical and it should be downwards. So if you remember these three things, you can draw gravitational force for all objects. So you see, even if I were to tilt it this way, it does not affect the way I draw my gravitational force. It will still be from the middle and it's vertically downwards. So these two lines are in the same direction, even though the boxes may be tilted differently. Okay, don't forget to draw the arrow and don't forget to label. Now, the next kind of force is a normal contact force. The word normal simply means 90 degrees. Okay, in physics, normal means 90 degrees. So that's why, so basically normal contact force means that when two objects are in contact with one another, right? They are in contact with one another, then the object, so let's say object A and object B. So maybe let's call this A, and this is the ground, which is also an object, so that's B. So when A and B are in contact with one another, A will experience a normal contact force by B, and it's 90 degrees and is acting towards A. So if I ask you to draw the forces acting on A, you should draw the normal contact force towards A. And which object is exerting this force is actually B exerting it. Okay. remember the rules, it should always be perpendicular to the surface. So can you see all this drawing, even though boxes may orientate differently, but it's all 90 degrees. And it should be towards the object. So you see the object, so towards. So the arrows go towards the object. So this is the rule to draw normal contact force. Some students will ask, where do you actually draw it? Well, you draw it near to the center, but maybe not to overlap with gravitational force. So leave a little gap, right? Maybe I can just show you. So if let's say you have a box here, and if you are drawing the gravitational force this way, then to draw your normal contact force, then just leave a little gap like that. Oops, sorry, it's not coming up. Wait a minute. Yep. So leave a little gap, and that's your normal contact force. Okay, so you can see distinctly the two. Because when you draw this right in the middle, then they kind of form one straight line, and then it's hard for me to see where you actually start drawing, because I need to know that you actually draw from the surface, and it should be 90 degrees. Let's move on. For friction, it's always opposite to the direction of motion. So if the object is moving to the right hand side, the friction will act to the left hand side. Okay, and even when an object is not moving, then there is also friction. Say for example, this object, although it is at rest, but if you put an object on the slope, naturally it will want to slide down. So that's what I mean by tendency of motion. That means there is a tendency for this box to slide down, but it is not sliding down because there's a friction that's acting upwards. So you always draw friction opposite to the direction of motion, and you draw it along the surface, right? Along the surface. So what does along the surface mean? It means you draw it, there should be some area where some parts of the arrow which is in between. So I actually prefer this to be this way. So you see this part here is showing the in-between surface. Okay, so maybe this one you extend a little bit, this one you extend a little bit, things like that. Okay, so that's how you draw friction. So let's quickly go on, and then we can take a look at the rest of the questions. And the last force that you need to learn how to draw is tension. Now, tension means that you're applying a force through a string or a spring. One thing about tension that you need to remember is it should always be acting away from the object. Because let's imagine, so let's say you have a box here, then there's some strings, loose strings here. Now, if you want to apply a force, you want to pull the string, then the string straightens, and then your box can move, right? So when you apply a force along the string, the force is acting away from the object, so you can pull the box. But if let's say the string is, let me finish the drawing. So let's say the string is here. Now, do you think it's possible for you to push the box using a string, like a raffia, or rope? You can't. You can't push through this string like that. The string will never be taut and will never have a tension. So it is impossible to apply a tension force for a push, only for a pull. So therefore, in this case, if you look at all the answers, all the drawings here, the tension is away from the object. Even when you hang a pendulum, okay, the tension is away from the object. And the reason why this pendulum, in fact, is able to stay stationary is because this tension and the gravitational force are the same. So this tension force and the gravitational force, the values are the same. So up and down same. So the resultant force is 0. And that's why your pendulum did not move. So now when you look at this diagram again, do you know what the mistakes are? You can pause to do the question, and then after that to play again to see if you'll get the answers right. So now the first one, the weight is drawn wrongly because the weight should always be vertically down. So it should be done this way. So this should be your W. Okay, so this is why it is wrong. And normal contact force, on the other hand, normal contact force should always be drawn, sorry, let me get my pen out. Normal contact force should always be drawn towards the object. So this is the normal contact force. Sorry. Right. Yeah, so this is the normal contact force. Tension, same thing. The mistake is for tension, right? You should always draw away from the object and not towards the object. Okay, so with lots of practice, hope you can remember the rules and apply the rules in all circumstances, regardless of how the object look like. So let's see if you're able to do this question. You have a ball that's rolling down a slope, and this ball, and you're supposed to draw all the forces. So in order to make this diagram neat, I'm going to draw the forces one at a time, then I'm going to erase it. But for you, you can draw all on the same diagram. Okay, so what are the forces? The first one that you should always remember will be gravitational force. So from the middle, right, we learn downwards. So this is gravitational force. So I can write the word, oops, sorry. I can write the word gravitational force. Sorry, it's gone. I'm going to draw again. Right? So you can either write out the word gravitational force. Okay, you can either write out the word gravitational force or you write the word weight. But do not just put a symbol like W. You have to spell it out if you're asked to do labeling. So I try to draw this as close to the center of the object as I can. Okay, so you have one force. I'm going to erase this. I'm going to draw the other forces so that it will not be untidy. And the other force is a normal contact force because the ball is in contact with the ram. So the part that they're in contact with always gives a normal contact force here. So this should be about 90 degrees. Okay, so this is the normal contact force. So two forces. Now, is there any tension? Don't have, because there's no string, right? So if you don't see any string, there will be no tension. Is there friction? Yes, there is friction because there's motion. As long as there's motion, there is friction. Now, this is when I sometimes see the whole class getting the answer wrong, because you see that the ball is rolling down. So the tendency for you is to draw the friction going up because the ball is going down. But I want you to bear in mind that this ball is rolling down a slope, a ramp, but it is a rolling motion. And rolling motion is different from a dragging motion. Now, this is when I want you to refer back to your notes. And there is one question about the wheels of a car. So please take note of that, the question and the answer. Okay. Again, a reminder, all the teacher's slides are found in Google Classroom under the respective topics. So if you want to get answers to the slides, go into Google Classroom and then you open up the teacher's slides. It has all the answers. So make sure your slides, your handout, all your blanks are filled up. Okay. So now this board, in order for it to roll downwards, maybe I just draw a bigger version somewhere here. Okay. So just draw a much bigger version. So for this ball to go down, we expect the ball to actually be rolling this way, right? So this is the motion that the ball should be rolling in order for it to go down the slope. Now, if the ball is rolling this way, I want you to see very carefully this part here, which means this part is actually going like that. Okay, the motion of the ball is this way, up this way, and therefore friction should be opposite to this blue arrow. Friction should be going down. Now this is not an exception, because just now I said that friction is opposite to the motion. So the motion will refer to this part of the motion, not just looking at the ball on its own, you know. So in order for the ball to go down, it will have to roll in an anti-clockwise anti-clockwise manner, which then means that this part here of the ball is rolling this way, and so friction is here. So for you, when you're doing this question, you have to do something like that, and there is friction. So you can draw all the three: friction, gravitational force, normal contact force, all on the same diagram. Okay, so This is because of the word rolling. It's a ball rolling down, so you have to have other considerations. Right, so I'm moving on to mass and weight. And important thing about this part is that you need to know what is the difference between mass and weight. You need to know its definition, you need to know um, the units, and you need to know what is used to measure them. So the definition, weight basically is the amount of gravitational force acting on a body. So in terms of definition, weight is amount of gravitational force. You measure how much gravitational force is acting on you. But for mass, that number that you see is a measure of the amount of matter in an object. Sometimes you can say it's the amount of substance in an object, because all objects are made up of atoms and molecules. So basically, how many of the molecules are inside, how big they are, this constitute to mass. You can measure mass. The SI unit for mass is in kilograms, whereas the other one is weight is in newtons. And the instrument that you use to measure is also different. Weight is measured with a spring balance, and mass is measured with either electronic balance or beam balance. This is a beam balance, but there's another kind of beam balance which I'll show you later. Okay, so this slide is important, the differences between mass and weight. And one of the questions that students often ask in this chapter is, what is the difference between gravitational force and gravitational field strength? Because you would have seen the word gravitational field strength when you are revising. So is it the same as gravitational force? Well, and to do that, I'm going to use an analogy of apples. Okay, so it's nice to see something non-physics here. So I'm going to use the analogy of apples. Now, if you are buying apple, okay, you go to NTUC and say, hey, one apple costs 50 cents. So I know that 50 cents is what we call the unit cost of an apple. Okay, the unit cost of an apple. Now, once you know the unit cost, you will be able to know what is the cost of apples, depending on how many you buy. So if you decide to buy 1, 2, 3 apples, then you just take 3 multiplied by the unit cost, and then you get 150. So you say, oh, the cost of the apple is $1.50. Another person may decide to buy 5 apples, 1, 2, 3, 4, 5, and you just multiply by unit cost, and you say, oh, the cost of the apple is $2.50. So you notice that the cost is not fixed. It depends on how many apples you are buying, correct? But it also depends on what is the unit cost. If they decide to have a increase, and each apple costs 70 cents, then the cost of the apples will also change. So you first need to know how many apples you're buying, and then you need to know the unit cost. Now, this is very similar to gravitational field and gravitational field strength. I'm going to write them side by side so that you can see. So what exactly is gravitational field strength? Now, we know that all the objects near the Earth has a gravitational force acting on it. Okay, so a 1 kilogram mass, the Earth will pull it down with a force of 10 newtons. That's gravitational force pulling up a 1 kilogram down. So this every 1 kilogram, the Earth will pull it down with 10 newtons. So therefore, I can say that the gravitational field strength, all my examples are going to be on Earth first, okay, before we start to bring in the other planets. Gravitational field strength is 10 newtons per kilogram. This is very much like the unit cost, because in unit cost, I say 50 cents per apple. So now it's 10 newtons per kilogram. Every 1 kilogram, the Earth will pull it down with 10 newtons. So knowing this, oh, by the way, the symbol is a G, italics G. So knowing this, if I now tell you that I've got 3 kilograms, are you 3 kilograms? Something like a model drawing, yeah? So if I now tell you I have 3 kilograms, are you able to show me how much gravitational force is pulling it down? You can, right? Because every kilogram, the Earth will pull down with 10 newtons. So when you have 3 kilograms, you will know that the gravitational force will be 30 newtons. So this is now called the gravitational force, not gravitational field strength. Gravitational field strength refers to 1 kilogram only, just like unit cost refers to 1 apple only. The cost can be 3 apples, can be 5 apples. So if you know the gravitational field strength, you can work out the gravitational force for any masses. So, oops, sorry. Okay, so you can work out the gravitational force for any masses. So if you have 5 kilogram, 1, 2, 3, 4, okay, 5 kilograms, you will know is 5 times 10. So that's 50 newtons. So that is again the gravitational force. This is gravitational field strength. This is the mass. All right. So the gravitational force depends on two things. It depends on what is the mass. The more mass it is, the larger the gravitational force. And then it depends on the gravitational field strength. So gravitational force basically is the attraction force between two masses. Now, in this chapter, we focus on one mass being an object, the other mass being the Earth. Okay. Gravitational field strength is the gravitational force, but it's acting only on 1 kilogram of mass. And very importantly, in this chapter, the formula W equals to mg. So to find the weight or the gravitational force, you need to take the mass multiplied by gravitational field strength. So back to the analogy of the apple, it simply means this mass is like the number of apples you're going to buy, and G simply means like the unit cost. Okay, pause the video, read the question, and see if you could answer this question. You have a spring balance and a beam balance used to measure. So a spring balance. So this is a spring balance, and spring balance is used to measure weight. This is a beam balance. So this is a beam balance, and it's used to measure mass. Okay, so this is to measure mass, and this is used to measure weight. A spring balance is also known as a Newton meter. Okay, so which statement is correct? When you do this experiment on Earth and then you go to the moon, well, when we go to the moon, the mass remains unchanged. You must always remember that mass will not change with location. So when you go to the moon, you will find that this reading here will be the same. The reading on Earth and on the moon will be the same. But when you go to the moon, it has a smaller gravitational field strength, so the weight will be smaller. So the reading that you see on the spring balance will therefore be smaller. In this case, the only correct answer is this. Okay, the beam balance shows the same reading on Earth and on the moon because the mass is the same. The rest of the options are wrong. Okay, because like for example, it says spring balance show a smaller reading on Earth. Not true. The spring balance should show a bigger reading on Earth because the Earth you will have a larger weight. This child is moving up a rope. Now, the reason why she's able to climb up, now, if there's no friction, the girl will definitely slip and go down. Just imagine you're holding a metal pole and then it's coated with oil. There's no way you can climb up because there's no friction. So the reason why she can climb up is because there's friction, right? And the friction will be, and the weight of this girl will be actually pulling her down. So the reason why she can continue to go up is because there is a frictional force that's acting upwards that will prevent her from slipping. Okay, so that's why the answer is the frictional force acting upwards. The frictional, because she has a tendency to slip. And then the last slide. Now, the question show electronic balance with some nuts, and this is the reading that you see is 26.90 grams. I'm not sure whether you can see the grams here. Okay, so it's 26.90 grams, and Right. So the question asks, what is the mass of the nuts on Earth and on the Moon? Well, in the first place, this is an electronic balance, and electronic balance measures mass. So electronic balance measures mass, and the mass is 26.9. Mass will not change whether you're on the Moon or on the Earth. The answer is the same. So 26.90 grams. You can convert it to kilograms if you want, although they didn't say you must give in SI units. The next one, what about the weight? Well, to calculate the weight on Earth, so the weight on Earth is the mass multiplied by the gravitational field strength on the Earth. So this is 26.9, but I'm not going to put 26.9 because I must remember that to use this formula, my mass must be in kilograms. So mass is in kilograms. So I divide by 1000 and then multiply by 10. And then I will get 0.269 newtons. Okay, and to find the weight on the moon, let me say another color. So to find the weight on the moon, I'll take the mass multiplied by gravitational field strength on the moon. So same thing, 26.9. To use this formula, mass has to be in kilogram, okay? The gravitational field strength on the moon is 1.7. Sorry, I think I should have written it in this question. You don't need to memorize the moon's one, but this 10 you need to, okay? So times 1.7, and then you will get 0.0269 times 1.7, 0.04573. So I'll write 0.0457. I stop here because I can only give my answer to 3 significant figure. Okay, there's a 3 behind in your calculator reading, but I must give my answer to only 3 SF. So I'm quite happy to just give my answer like that, right? Now, if you are still with me at this slide, I applaud your patience. And it would be good for you to actually test your understanding. If you could go to joinmyquiz.com, there is, and then you key in this 3688466, you will be able to do an online quiz and to test whether you understand mass and weight. Okay, so it's a 10-question short quiz. So enjoy doing this quiz, and from the score, you should know whether you understand or not. Okay, so if you have any issues, please reach out to me and I will be able to give you consultation via Zoom. All right, so all right, I got to record the next video now. Okay, see you.